All right, so today we're going to talk about empirical formulas and molecular formulas. We've been talking about this in class a little bit, so hopefully you have a good idea already. But the empirical formula is the most reduced formula that you can have. So it's not not necessarily the actual chemical formula of what we have, but it's the ratio that's been reduced down of how many of each atom we have in the formula. So it's possible that you had the formula C4H8, that would get reduced down to CH2. That would be the empirical formula. The molecular formula is the actual formula that we have, right? And so the molecular formula would be the C4H8. It's not reduced down, it's the actual formula there. So if you look at these few examples here, the first one, CH2O, that's as reduced as you can get. You can't divide that by anything more. The two, carbon and oxygen, have a 1 subscript there. Hydrogen has a 2. So that can't be reduced. So that's the empirical formula for that molecule. This is an empirical formula. Nothing can be reduced. 3 and 8 aren't divisible by each other. Here for this formula, each of those numbers, each of those subscripts is divisible by 2. So this is a molecular formula. If we want to know what the empirical formula for it was, we would reduce it down. Divide each one by 2. C2H4. So then if you look at this bottom equation, CCH32, that's telling me that I have 3 carbons and 6 hydrogens. So that is not an empirical formula. If we want to reduce that down to an empirical formula, we can say CH2 because they're both divisible by 3. So that there is the actual empirical formula. Now it's really important that you understand that an empirical formula can sometimes be a molecular formula as well. So for instance, if you have the molecule H2O, that is both an empirical formula, it can't be reduced anymore, but it's also the molecular formula. In H2O, there's literally 2 hydrogens bonded to 1 oxygen. So we're going to go through a couple sample problems here, one easy one, one hard one, to try and make sure that you are ready to go here. So we're going to look at this bottom one that says determine the empirical formula by of the compound containing 37.5% carbon, 12.5% hydrogen, 50% oxygen by mass. This is page 41 in your packet if you want to follow along. So we can't compare weights. The weight of a carbon doesn't compare to the weight of an oxygen, the weight of a hydrogen, and the weight of anything else, any other atom. That would be like comparing the weight of a bowling ball to the weight of a feather. Just because you have 37 pounds of bowling balls and feathers doesn't mean that they're equal in how many you actually have. If you have 37 pounds of those two things, you probably have way more feathers than bowling balls. So what we do need to do here is we need to figure out how many moles of each of those substances we have. So in order to do that, we're going to make an assumption. And that assumption is that since we have a set of percents here, we're going to assume that we actually have a 100-gram sample. And if we have a 100-gram sample, 37.5% of it's carbon, that means 37.5 grams of it are carbon. And 12.5% is hydrogen, so 12.5 grams hydrogen, so on and so forth. The last one, 50 grams oxygen. All right, so my first step is going to be to convert each of those into moles. So the molar mass of carbon, 12 grams per mole. The molar mass of oxygen, 16 grams per mole. And I want to keep everything nice and labeled so that it's easy to follow. The molar mass of hydrogen is 1 gram per mole. So I'm going to put those in my calculator and show you the answers here in a second. Alright, so I stuck those in my calculators. I got 3.125 moles of carbon, 3.125 moles of oxygen, and 12.5 moles of hydrogen. So what I need to do now is I need to set up a ratio. And this is where on the quiz a lot of people were having trouble. So a lot of people would recognize right away, okay, I have the same amount of carbon and hydrogen. And that's true. So that means for any carbon I have, I need to have one oxygen. But what I want to do is I want to set up a ratio between the hydrogen and the oxygen. A lot of people were saying, okay, well, I need to multiply the oxygen by 4 to get the hydrogens. So that means there need to be 4 oxygens. That's not true. This is how much we have. So we want to compare how much we have to see what the ratio is. So if we have 12.5 hydrogens and 3.125 oxygens, then if we put that in our calculator, let me make sure I'm doing my math right, we get 4, right? So what that tells me is 4 hydrogens for every 1 oxygen is what we actually have, right? So then we're going to assume we have 1 carbon, which means we also have 1 oxygen. And if we have 1 carbon and 1 oxygen, we said 4 hydrogens for every oxygen. So my empirical formula there is going to be C4 or CH4O. If the question then asks, hey, you have a molecular weight and the molecular mass is going to be 64 grams per mole, what's the molecular formula? Well, how I'd figure that out is I'd say, okay, well, I know my empirical formula weighs 12 plus 4, which is 16, plus 16, which is 32. 32 is half of 64, so this empirical formula is half of the actual formula. So the molecular formula in this case would be double, C2H8O2. Well, we can really crank up these problems. So this is problem number 5 on the lab you did. It says when 4.76 grams of organic compound D, which contains only carbon, hydrogen, and oxygen, is burnt, we get a certain amount of carbon dioxide and water. And it wants to know what the empirical formula of D is. So D is our hydrocarbon. If you remember combustion reactions, which I hope you do, hydrocarbon reacts with oxygen to make carbon dioxide and water. All right? Well, all the carbon, our hydrocarbon has carbon, hydrogen, and oxygen here. All the carbon in the products must have come from the reactants. And there's only one reactant that had carbon in it, and that's D, the fuel. So, according to the law of conservation of mass and matter, if we can figure out how many moles of carbon were in carbon dioxide, we know how many moles of carbon were in D. The same with the hydrogen. All the hydrogen had to come from D as well. So if we can figure out how many moles of hydrogen were in H2O, we know how many moles of hydrogen were in D. So at that point, all will be left to figure out is how many moles of oxygen were there. Then we can set up a ratio and get our empirical formula. So I'm going to start this problem off and then come back together with you. Alright, so if you can see my work here, right here, I took the amount of carbon dioxide that we had and I turned it into moles by dividing by the molar mass of carbon dioxide. And that came out as 0.238 moles of carbon dioxide. I did the same for the water. I took water divided by its molar mass, got how many moles of water I had. Now, this is where the problem differs a little bit. If I have 0.238 moles of carbon dioxide, that means I have 0.238 moles of carbon, because every 1 carbon dioxide has 1 carbon in it. So this is a perfect matchup. But every H2O does not have 1 hydrogen in it. Every H2O has 2 hydrogens in it. So if I have 0.317 moles of H2O, I have twice as many hydrogens, because there's 2 for every 1 H2O. So that's going to be equal to 0.634 moles of hydrogen. So that leaves us with the question of how do we get the moles of oxygen? And there's actually a couple different ways that you can do this. However, I'm going to show you just one method, what I think is the most useful method. So if I know that there's 4.76 grams of D, what I can do is I can figure out how many of that 4.76 grams is coming from carbon, because I know how many moles of carbon I have, and how many of that 4.76 grams is coming from hydrogen. If I can figure out what carbon and hydrogen are, then I can solve for my unknown, which is oxygen there. And I'll be able to figure out how many grams of oxygen I have, and then I'll be able to convert that back to moles of oxygen, and I'll have moles of all three atoms, and I'll be able to set up a ratio and find the empirical formula. So I'm going to do that now. Okay, so I figured out how many grams of carbon I had and how many grams of hydrogen I had by multiplying by the molar mass. All right, and so I figured I had 2.86 grams of carbon, 0.64 grams of hydrogen. If you remember, we said D, which is made up of those two elements plus oxygen, weighs 4.76 grams. So if I add up those two, I get 3.50 grams. All right, so 3.50 of the grams are coming from carbon and hydrogen, which means that 1.26 grams are coming from oxygen. So now I am going to convert that back into moles. I have moles of carbon right there, moles of hydrogen right there. If I figure out moles of oxygen, then all of a sudden it's turned into an empirical formula problem like we've been doing. So I took my mass of oxygen, converted it into moles there. So here's the moles of all three of those substances. So now what I want to do is I want to set up a ratio. I'm going to use the smallest number as the bottom or the denominator of my ratios. So if I'm comparing carbon to oxygen, it's 0.238 to 0.0788. If I'm comparing hydrogen to oxygen, it's going to be 0.634 to 0.0788. You always want to compare to the lowest number because that's going to make your comparison a big number to 1. All right? If you do it the opposite way, it gets really confusing. So I suggest always make sure you put the smallest number of moles on the bottom. All right, so if you look here, I set up my ratio. I got 3.02 carbons for every 1 oxygen. You're allowed to round here, and again, this is where there was a little confusion. You can round if this ratio comes within 1/10 of a whole number. So 3.02 is within 1/10 of 3. So I'm going to round that to 3 carbons for 1 oxygen. If it doesn't, then you need to actually multiply until you get that whole number ratio. So for every 3 carbons, I need 1 oxygen. Down here, same idea. I got 8.05 hydrogens for every 1 oxygen. That's close enough to round to 8 hydrogens for 1 oxygen. So now if I write my actual formula, I'm going to pretend like I have 1 oxygen. If I have 1 oxygen, right above it tells me 8 hydrogens and 3 carbons. So my empirical formula is C3H8O. So a lot of work, but actually not too difficult once you kind of figure out the pattern. So I hope this helps a little bit. We'll continue to talk about this in class and make sure that you look through the practice problems.